Well, good morning, evening, afternoon, whatever the case may be. Um, oh, we got cool. We got Ian on too. I'm Matt Dupuy from ARM. I'll be helping moderate your. This is just going to be a very informal office hour session with Pete Warden and Ian Napier from Google. You probably already know this is these guys represent TensorFlow Lite for microcontrollers at Google. Um, if you have any questions, we're happy to let you either unmute or ask, or we can just go through chat and I can relay the messages and have a fairly free-form discussion with some of our experts here. So, Pete, can you introduce yourself?
Sure, yeah. Thanks, Matt. And yeah, I'm Pete Warden. I'm the tech lead on TensorFlow Lite for microcontrollers here at Google. And yeah, I'm looking forward to hearing what we can help people with.
And Ian?
Hi, I'm Ian. I work with Pete. I'm the product manager on TensorFlow Lite for microcontrollers. And yeah, happy to answer any questions or respond to any thoughts people have.
Thank you both for joining us. I'm guessing a few of the people in chat have attended some of the other sessions for TensorFlow Lite Micro, so I expect maybe we'll have some follow-up questions from yesterday. But yeah, please feel free to ask any questions in the chat box or unmute yourselves. All right, quiet so far. Please feel free to jump in at any point, but I'll ask a few questions. Some of the generic stuff that I've been following just as an outside passionate nerd. It's been not rooted in artificial intelligence. A lot of the work that you guys have been doing has been making AI and ML accessible for more embedded people like me. And I mean, the obvious overarching goal in TensorFlow Lite for microcontrollers has been, platform abstractions and being able to run on as many operating systems and platforms as possible. And that's, I think, one of the coolest things that you've really accomplished. But in terms of future roadmaps, what are some of the other big things you would like to accomplish with TF Lite Micro?
I mean, really, we exist to help people create cool things. And we've had some cool use cases, and we've have a lot sort of bubbling away that we're going to be coming out of Google in the future and from other companies we're working with, but really getting more use cases out there and getting more more products actually using TensorFlow Lite Micro. And that's where these sessions are really useful, is because we actually get to hear what the things that people really need are. The sort of the goal of TensorFlow Lite Micro is almost to kind of like fade into the into the hedge and sort of disappear and just be and let people just kind of train models and just like deploy them without really worrying about it too much. So
do the Homer meme and let the community guide
yes.
the direction a little bit. Yeah. Cool.
Exactly. Looks like we do have one question on chat. So go ahead, Ian.
I was going to say, just like a major thing on our roadmap for the rest of the year and next year is our continued work with ARM on the Simpsons optimizations. And the more these sort of come transparent under the hood without a developer having to worry about them, the more we deliver on performance with portability across Cortex-M chips. And so, this means that people who are building with TF Micro, you get to focus your time and energy on building features and thinking about your overall product, and less about the bits underneath that make it all work and are performant. And hopefully we're the ones worrying about that, not you. And so that's going to be a big piece of our roadmap for the future.
And that I will invite those that are here right now to check out the session that Pete did yesterday. That should be posted online. He did a very practical session mixed with some of the optimizations we've been doing, just to make things accessible for those that don't want to do the hand optimizations and show really the performance gains and what we're expecting. So one of the questions, or the first question in chat from Andreas is, yeah, my company's working on some self-learning algorithm for current detection in BDC motors. Does TensorFlow support these kinds of sensoric and sensor data? I guess, it continues to say, so you aim to make TF small enough footprint for CM4 or similar device. Yeah.
And so on both those, there's any, you can take any kind of sensor input data and run it through TF. There's not a limitation on what type of sensor or what type of input you use. And many folks are using multiple sensor inputs simultaneously with sensor fusion to use neural nets to compute simultaneous sensor inputs as well. So there's not any kind of limitation. And looking at current detection on motors is something that we have heard about.
That's something we've seen a lot in embedded industry is the transition from really algorithmic based, academic based motor control systems to more AI based, that modeled in 3D systems and physics engines first, very heavily first, and then.
Can you guys hear me actually now?
Yes.
Yeah.
Ah, perfect. Yeah, sorry, I was the guy in the chat. My name is Andy. Hi. Well, I'm specifically aiming at this question because we are currently working on a project that aims to completely minimize the test frameworks that are used for BDC motors in the automotive applications. The huge problem now is that we need a huge mechanical setup to simulate the forces on the motor. We have to build a one-on-one model of a door or something to simulate the stresses the motor has to go through. And we are working on a self-developing algorithm that can actually measure the torque and the current input and then detect if the motor is behaving inside certain quantities, certain limits. And the huge problem is that we don't have many data. That's why we actually have to learn this stuff. That's the customer is not very happy because we were so we need a torque sensor and we need a speed sensor and we need a current sensor. The customer was so, well, do you have a current sensor? There you go. That's all you get. And so we are kind of trying to completely simulate the torque on the motor by just measuring the current. And we just have current and speed of the motor. So that's really not a lot of data to go from.
That's a very interesting problem, and what I guess I would love to know is if you're able to, I think I said I might have said in our in the workshop, the biggest challenge for creating these deep learning models is getting enough labeled data. Now, if you're actually able to have something where you actually measure the torque alongside the current and the motor speed, and you're able to actually in TensorFlow or another deep learning framework, but TensorFlow would be easiest for porting to TensorFlow Lite Micro, actually predict the torque based on just those two inputs. I feel like that would be the biggest thing, the biggest hurdle to overcome, because once you have that model, I'm hoping that porting it over to TensorFlow Lite Micro should be, it'll be some work, but it would be fairly low risk. It sounds like the highest risk thing is can you create a model to do that?
So probably the best way would be to like stupefy it down, like build one mechanical model, get like super labeled data from there, feed the TensorFlow input with it, and then run it on my simulation. Like the system we are building that just simulates the stresses on the motor.
Yeah, exactly. And just see, like, the more, create as much labeled data as you can, and then just see if you can create on like the desktop side, in Python, can you actually do a good job predicting what the what reality actually is, and if you can, then I think you have a very good chance of being able to kind of turn that into a TF-Lite micro model.
Okay, yeah, that's very interesting, yeah.
And I'm happy to. I was going to say, I'm happy to, take any of these discussions offline as well. I'll just put my email in the chat here, and like I was saying in the first question, one of the biggest challenges we have is like finding more. Like, we have a bunch of use cases, but we want more. So I'm happy to sort of email back and forth with people who have interesting use cases like you, Andy.
I'm already sending you an email. I'm just sending it out there because otherwise I will forget.
Yes, perfect.
Yeah, because I think this is something that we really need machine learning for, because as it stands at the moment, the customer has to make like a huge mechanical model for all its motors it's trying to analyze, and he has like a huge variable analysis he has to run, and he also has to run them in climate chambers. So if we have like data models of each mechanical model, and we can simulate them on only our stress benches, the stress benches take like a tenth of the room, I think this would be a pretty nice use case for what you're offering here. Now the next question is, as I was also following up in chat here, can we make this whole thing small enough to fit on a CM4?
Yeah, so we actually we've even run some stuff on M0s.
Okay, nice.
Yes. So we're down at like 20 kilobytes is the sort of the base binary footprint. So that's kind of the flash size. And then we can run in as few as a few kilobytes of RAM. And for example, we have several pieces of sample code showing different models. One of them is a voice recognition system that recognizes yes or no, and that has like a 20 kilobyte model and takes a few K of RAM. We also actually have an accelerometer based model, and I have this magic wand here that I strap an Arduino Nano to, and use the accelerometer to actually detect different sort of gestures.
Like if your Leviosa is correct.
Yes. And that one is that's also a very small model, like just a few kilobytes. So yeah, we're definitely like the M4 is actually, we fit in there pretty comfortably. You start getting down to M0s, and some of them only have 16K of flash or something, and that starts to get tough. But we have figured out ways to work in some of those environments. But yeah, the M4 is what we do most of our demonstrations on, and we're very comfortable with that.
Okay, so the big hurdle is getting this labeled data for me, because as I said, the customer is not very happy with extra sensors.
Exactly, and like getting the model, like figuring out how to solve this on the desktop, in kind of using pre-recorded data and like getting labeled data. I feel like that's the most risky thing here. That's the part that I don't have any insight into.
Yeah, but that's really interesting, because I actually never thought about that. We were just going out from the current data and the speed data we had, and we had to make like a stupid model that has to predict like, so yeah, this current could be in range, but we have no actual torque. It's like we are just like regulating from behind.
Yeah, exactly. I think if you're able to gather the torque data together with it, and then just feed in the current and the motor speed, and see if you can create a model that estimates the torque, and if there are any other variables that you can feed in as well, I'd just be interested. It's a really interesting modeling problem, I feel like.
Yeah, because
what are the different tolerances on different motors and from different batches, and that to me is the harder part. Once you have the model, quantizing it, compressing it, doing that's kind of guess and check and see what you can fit into your accuracy needs. But yeah, getting the data first. Yeah.
Okay, so the best thing to do, the best plan of attack would be like make one run with as much data as I can, and then feed the model just with the data I can provide in the next step, and the model will probably just guess its way through.
Yeah.
I mean, yeah, I know it all sounds kind of vague. It's because I have some strict NDAs and stuff, and.
Oh yeah, no, I totally exactly that's yeah, but that in general terms that sounds right. Sort of.
Okay. Is there like a prototype or something, or like can I just use this model somewhere because I've seen it's open source? Like, is there just like for development purposes that I can try it out? Is that possible?
So I mean, yeah, you can definitely. We have, and actually we have sort of some documentation. There's the TinyML book as well. I'll just plug that. I put that in the chat. That's like a 500-page O'Reilly book that has a lot of examples and like walks you through how to get this up and running on something like a Cortex M4. And we'll also actually have you can use the Arduino IDE if you're familiar with that as well. Like that can be an easy way to get started in prototyping. And we'll have the video recordings and slides of my workshop from yesterday that talked about that too.
Oh, perfect. Thank you very much. So, yeah, that's pretty much everything answered. Everything else would be too much detail at the moment. Please, the other people can also pick up where I left off.
Great.
Yeah, I was going to say, we have we're going to try and break these up into 20-minute blocks with 10 people. We've got about 20 people in the waiting room. So does anybody else have a question?
I just wanted to add to Andreas, though. I think you actually have an example of where neural networks are potentially a substantial benefit because you have a continuous pipeline of data coming back in too. So, one thing you might talk to your customer about is the effort upfront might be well worth it because your model has the potential to improve over time as you collect more data from the field and sort of keep on feeding that to retrain your model over time.
Well, yeah, then I have to think about CI and CD cycles, and our customer is not very firm with embedded software. For them, it's like a huge magic black box we're developing. Okay, yeah. Well, but yeah, that's a good idea. Probably just get like some log data out and everything that I can just then feed the log data back into the models. Well, somebody has to pay for it, so yeah. Let's see. All right, I leave the stage, and thank you very much.
No, thanks, Andy.
Thank you. And welcome to those just joining us now. We have Pete Warden and Ian Napier from Google, both from TensorFlow Lite for microcontrollers. We've been pretty informal here, so I invite anybody joining to either ask questions in chat and I can relay them, or they can read them, or better, I think, is just to unmute yourself and ask your questions. There's nothing new popping up. A follow-up with Pete's book is, yeah, I got early access to it, and it is a great primer. But also the documentation in the GitHub repository for all the examples for getting things down to smaller microcontrollers is getting really good now. You can follow pretty much any of the examples as sort of a primer to educate on different operating systems and RAM considerations and power considerations. So so many projects out there with garbage documentation exist, and this is not one of them. So I'm really happy to have that.
Oh, no, thank you. Yeah, we're still, it's one of our priorities to keep improving that, actually. We're still not still not happy. I'm glad it's working better, but there's still look at it, and there's lots of stuff that we want to sort of expand out.
Do more. Yeah, please feel free to jump in, unmute yourselves, ask any questions. Of Ian and Pete can go really technical or go really high level with what we're expecting from the future, or what overarching goals are. And so this is the time to ask.
So there's a question from Gregor. Yeah, and maybe I'll read it out. So I want to use another Cortex-M4 microcontroller for TinyML, a different one than used in your book. The information in the book was not enough to do that. Are there any further guidelines on how to do this? So yeah, this is definitely an issue we see, especially because there are so many different IDEs and tool chains that people are using. We are trying to work like actually Matthew's doing a lot of great work around trying to improve how we deploy TensorFlow Lite Micro into some of the ARM-based IDEs. Maybe are you able to unmute yourself, Gregor, and maybe we could chat a bit about what the specific issues we were running into and what the specific platform that you were focused on was?
Yes, hello, this is Gregor. So I just wanted to use the microchip Cortex-M for some D51, but when I saw all this, what is described to trickle port 1 from the TinyML book, that was not clear enough for me to do this. And I'm not sure if it is very easy now to say what to do, but yeah.
So what tool chain are you using? Were you just using GCC and makefiles, or are you using like Kyle or Embed, or?
I used also GCC, so I tried different way. I tried also used only GCC, and then tried to compile everything that worked, but then I was somehow stopped. But this was already some time ago, so I can't remember any details now.
All the details, yeah. So yeah, I would love to, if you do, blow the dust off that work, I would love to know where the errors were after you, because in theory, what we aim to do is let you just take the source files and compile them, and they should work for your platform. You should just be able to add them to your makefile or whatever you're using to compile using GCC, and things should, in theory, just work. Now, in practice, there are still some rough edges, but we'd be happy to help. See if I can, offer some advice to help you actually get up and running. So I've just put my email address in the chat, so you feel free to, drop me an email, and I'll be happy to see how we're actually able to help.
Okay, thanks. Then I will try it again.
Awesome.
It is a very fast-moving project.
Yes.
the latest versions have radically changed the way they build, and have become the makefiles have spec'd out a bunch of different platforms that didn't exist before, and they've gotten easier to use. And yeah, it's definitely worth revisiting if it's been, even a few months.
I was wondering if you guys can help with delegates. Hi, this is Patrick. So you guys have these delegates available right now where I think you guys are supporting GPUs and I think another DSP or something.
Yeah.
My company is working on an AI chip as a separate chip away from what the processor would be. And I was wondering how we could use, or is there something there where it's a sort of generalized, you know, it's not just GPUs as delegates, it's something that is sort of custom to you.
So are you targeting microcontrollers or like Cortex A sort of type systems for
So
your
like
accelerator?
for now, our goal is to do, to put this AI chip next to some single board computers. So like a Raspberry Pi or an Arduino, where the AI workload is being done over on our chip, and then some of the other stuff is happening. Whatever our AI chip can't handle is being done with TensorFlow Lite on the actual processor.
Yeah, and the reason I'm asking is because, like with the Raspberry Pi, because that's able to run Linux, you can run full TensorFlow Lite for mobile. And what I'm focused on is just running TensorFlow Lite on the microcontroller side. The reason that's pretty important for the delegate stuff is the reason delegates exist is so that at runtime, the framework can actually decide, oh, I've got this hardware available, I'm going to offload some of my work onto the GPU or onto the, you know, Qualcomm DSP, mostly because that's a situation on Android where you ship one Android package and then it has to be able to adapt to whatever the user's phone is. Now for micro, when you know, for embedded use cases, you pretty much always know exactly what hardware you're going to be deploying on. So you don't have to do that decision at runtime. And so we use a different approach there where we actually expect people to offline replace parts of the graph with custom ops that run on the accelerator.
Okay, yeah, that's what we're gonna do.
Yeah.
There would be a nicer way of doing it, but
yeah, and we are trying to make that a bit more user friendly, because, for example, it's how the Ethos accelerator on microcontrollers is supported. You know, there's a pre-processing step that takes a normal TF Lite serialized graph and actually goes through and in an offline tool like replaces the ops it recognizes with what, you know, a sort of a blob. But again, I'm happy to work with, you know, at least offer advice as you're like looking into doing this. So feel free to drop me an email, and me and Ian will be happy to try and help how we can.
appreciate it. Thank you, Pete.
Awesome. Looks like we have a question. Sorry, go ahead.
Yeah. Well, Andreas again asks, yeah, you said you can run parallel data streams. What about FPGAs with parallel ADC data? Can you learning?
Yeah.
I mean, in unlimited instances. Yeah, that's great. Yeah.
Yeah, that's a really interesting use case. And the nice thing about these deep learning models is they really are just math. And so we've tried to keep the implementation of TF Lite Micro as kind of dependency free as possible. You know, so without operating system dependencies or other things like that. So we have had people using FPGAs, especially soft core FPGAs, and running things like that. I haven't seen anybody doing it in parallel like this, but I don't see any reason why you couldn't do that.
Yeah, the software stack that they have allows for acceleration layers to be placed underneath, whether that's SIMD or FPGA or any number of different ways you could accelerate. And that's we'll plug the ARM SimSystem in there that exists underneath and accelerates some of the kernels with the SIMD that may or may not exist on any of the processor underneath. Yeah. And then, does that kind of answer what you're asking, Andreas or Andy? Cool.
Great.
And John asks, new to ML, can I use TensorFlow to optimize temperature and data center based on temperature sensors reporting to the cooling controller, the controller's ESP32?
So interestingly enough, I just pasted a link to a blog post from 2016 where DeepMind actually used TensorFlow and deep learning to optimize a whole data center and saved 40% on like cooling costs, which was pretty neat. Now, the way they were doing it, though, was they were looking at sensors from all across the whole data center, and then kind of using them to predict what would be happening. And the tough part was that it was a system that was very hard to simulate because there would be things like weather happening, there would be unpredictable like load, in terms of the amount of compute that was needed, and a lot of the like cooling systems actually had like long run-up times, so they would take some minutes or something to actually really start to have an effect. So it turned into a really interesting problem of trying to optimize this whole system with like thousands of sensors and thousands of things happening at once. Now, I would be interested to know more about your problem, John, because it sounds like you're trying to do it on more of an individual level. And I think as we were talking about in one of the earlier sessions, as long as you can create a TensorFlow model with like labeled data that can predict this, transferring it over to something like a controller isn't too scary. That's fairly low risk. Like the high risk thing is like, can you build a model to actually do what you need to do? And can you gather the data to actually train that model? So I don't know if that's helpful. And feel free to unmute yourself, John, too, if you want to sort of jump in and add some more, ask follow-up questions.
Well, you're absolutely
Wants
right.
to train while in production. Yeah,
it's hard to do that. Wanted to do it while it's in production, have a continually learning machine, and don't know if that's something that how to set that up.
Yeah, that's honestly, I would think about prototyping with something like a Raspberry Pi, because going down to the microcontroller level is great when you want to actually like scale up your solution. But usually the biggest problem is just, hey, how do I actually get a model that works in the first place? Yeah, that sounds like the first step. Can you prototype it using something that's easier to work with than an embedded controller?
Makes sense. Thank you.
And we had a question. Yeah, do you have any future clues about NN architecture? About how NN architecture will become very common in low-cost devices such as Cortex M0 or replace them. So we can use tiny ML and TensorFlow in low-cost solutions. Yeah, that's. I may ask Carl and Wei to jump in a little bit if they want to talk about things like M55 and Ethos and some of the lower cost stuff. I mean, the short answer is, at least from the ARM perspective, yeah, we're working on it, and there should be some stuff out pretty soon that is in the cost range of Cortex M0, but with SIMD accelerations and possibly NPUs attached as well. It just sort of depends on really what your specific power and tolerances are, or what your costs are. So yes, I guess is the short answer. It's there's a lot of people working on it. If you have any kind of specific questions about NPUs and SIMD, yeah, we're happy to try and address those. Cool. All right. And for those that have added in the last 10 minutes or so, you're totally welcome to unmute yourselves and ask your questions, or relay them in chat. And this is, we got Pete Warden and Ian Napier from Google, from TensorFlow Lite Micro. Yeah, let's see. New to TensorFlow Lite in the microcontroller can implement CNNs with large backbones like Inception ResNet.
So you can. The biggest restriction is how much memory you have on your microcontroller. So even things like Inception tend to have several million parameters, which means that if you're storing the weights as 8-bit, you need several megabytes of flash space, which is usually not feasible. So what we find is that people tend to want to use things like MobileNet V1, which is much smaller and doesn't really suffer much accuracy loss. And we have an example of doing detecting when a person is actually visible, which we did as our workshop, which I think yesterday, which I think the video will be up shortly. That uses a 250 kilobyte version of MobileNet. So, the short answer is you can definitely use a wide range of CNNs, but because microcontrollers have very limited flash normally, it's typical that you'll use a specialized, smaller architecture for that.
Let's say even a couple of years ago at Google Cloud Next, we put out a really quick and dirty proof of concept that could do basic on an M7 10 classifications, which I think is a really popular one now for microcontrollers, just because it's easy to say that's a plane, that's a horse, that's a car, that's that's just, like you said, that's a memory limitation more than anything else. I actually ran around like 10 frames per second on an M7 at the time, so that was. I'll have to go back and see what we can achieve now.
Yeah, with the SimSysNN optimizations, I bet there's.
Yeah. Huh.
And yeah, the follow-up was using larger backbones because you really need accuracy. Yeah, that may be a challenge. Like, we're able to, on the compute side as well. It depends what your sort of timing needs. If you can run for like 10 seconds, you can do almost any amount of compute you need. But if you need to run in like 100 milliseconds or something, there's a very limited cycle budget. And like the Ethos, M55 sort of stuff is helps with that, but you may still have to consider an architecture where you have a microcontroller that does kind of like a low fidelity version of the inference, and then wake up something more like a Cortex A7 system to do the more advanced, larger backbones if some condition is met. And that's kind of why we have the person detection as our example. Is often what people want to do is have like a TV or something wake up when somebody gets near. You want it to be always looking for people, but running at very low power so that it's not, you know, an energy vampire in the EU sense. But then when you actually want to do sort of, you know, gaze detection or full voice recognition or something else, you actually do that on a Cortex A7 that you've woken up, because at that point you can be in high power mode.
Yep, we're going to let some more people in now for the next chunk of time, but I'll say that again, just plugging Pete's presentation yesterday. That was a great example of we did person detection on a very low power processor, and that's, I think, one of the coolest use cases is that it's if you want to do something like facial recognition, but you don't want to be eating a lot of power, then you connect the camera up to a Cortex M processor and wait till you see a person first, and then wake up the larger processor, which is exactly what he just described. It's just but we're really fascinated with what other use cases you might have that would do something similar. They don't all have to be micro. It could be, yeah, that type of, you know, the micro's interrupting something that's bigger, but at least the small classification is done. So yeah, if you have anything, like if you want to unmute yourself or let us know in text, like what the application is and how we might, you know, brainstorm shrinking it into a smaller use case, that'd be a lot of fun. So I think we've let most of the people in the weight room in now. I'll just do a really quick hello and let you know we've got Pete Warden and Ian Napier here from Google TensorFlow Lite for microcontrollers, and we encourage you to ask questions in chat or unmute yourselves and ask away. There's really the topics can be really far ranging, from introductory questions to, since a lot of people are embedded software engineers here, to theoretical AI questions, to really roadmap stuff, what they're planning on doing. So please feel free. On the spot here, have you guys in the last few days heard any interesting questions that have come up in any of the other sessions that these guys might be able to answer?
I haven't, but I have a question. It's around, let's say, compilation versus interpretation for TensorFlow Lite Micro going into the future.
Yeah.
Because I just found out about the TensorFlow Lite compiler like 2 weeks ago.
So yeah, that's a really good question. It's something that comes up a lot. It's very common in the embedded space to do code generation for a lot of problems, and it has, you know, it does have some nice properties, and we're definitely really what we see code generation as is it's a nice potential optimization, but a lot of our product use cases, they need things like, hey, they need to be able to swap out models independently of the code, which is hard with code generation. They also often need to have multiple models in the same application. And when you do that with code generation, you often end up with a lot of duplicated code. So the binary footprint starts to expand. What we've also found is that it actually often makes it harder to get optimizations in, because you're going through this. It's very tempting to kind of make changes in the generated code to optimize things, and that's one of the advantages of generated code. But then you sort of have to, like when you have a new version of the model, you then have to figure out how to patch those optimizations that you put in back into the code that you just generated. So for all of those reasons, we've actually focused on the interpreted approach as like the starting point. And we are expecting that we will have more code generation going forward in the future. But hopefully a lot of the advantages of code generation you should be seeing still with our interpreted approach, like a very small binary size and few dependencies, really hopefully easy to build by just grabbing a bag of files and putting them into your build system. Because I know that's another advantage of code generation, is you just get like one big file and you just have to drag that into your IDE and you can just go. We aren't quite that easy, but we do try and make it at least easy enough to just grab all of the code you need and just drag it into your IDE as separate files and go. But so that's kind of I know it's a very active question at the moment, but that's kind of our thinking around it at the moment.
No, that sounds good. Like that's a very solid answer. And there's another question too. Let's see. In good timing, it's from Ram. Hi, what is the path to the companies to use TensorFlow Lite in their safety critical certified products?
Yeah, that is interesting. We have had some companies sort of like starting to look into this. I honestly don't know what the hurdles are going to be there. I think it also depends a lot on which industry you're trying to be sort of like safety certified for. One of the, I know, for example, I know with some medical devices and things, it's actually the whole nature of like machine learning has been tough, because you need to kind of explain a lot about what's happening with models. And having the lack of explainability that you get with these generated models has been tough. So I guess the answer is that we're happy to chat to companies that need to do safety certification. We aren't doing anything particular ourselves at the moment. I've just put my email in the chat for anybody who wants to send email questions and maybe wants to talk about things that they, if there's stuff that you can't talk about in a public chat like this. Yeah, we don't have a, we haven't spent much time on this yet. We're happy to work with people who are doing this safety critical stuff, but we don't have any existing guidance yet.
And I think we'd be happy to work with ARM's various customer relations and business development groups to help answer some of these questions if there are more specifics. So I think it would depend, as Pete was mentioning, on a specific customer or specific industry need.
Yeah, this is a kind of a passionate interest in the last few years of watching all this develop. One of the more interesting things, it's not necessarily safety critical related, but I think last year at TensorFlow World, there was a presentation on privacy and people trying to glean data from, they're indeterministic answers, but there are ways to leak information out, and Google was doing some really interesting things around privacy and security in that space. So there are definitely people at TensorFlow thinking about it, but we haven't really looked at it in the microcontroller space. So yeah, I'd be curious to hear yeah, if there are things you can share, or if we have to work on getting NDAs in place to discuss further, it's something we can definitely talk about. So yeah, I guess I should put my email address in as well. And while I do that, if anybody wants to unmute and ask any questions, please go ahead. So yeah, using it, ML embedded with the goal of bringing a microcontroller to recognize particular movements and particular sound DSP. What are the pros and cons of all the AI tools like PyTorch, TensorFlow, etc.? What is your or what roadmap would you recommend to dig in on this topic? Oh, that's a huge question.
I mean, I can definitely make. I mean, like I love PyTorch. It's a great framework. Use whatever you feel comfortable with, and like whatever you're able to use to actually get the the training side. To get a model that does sort of what you want on the desktop or in the cloud. Like that's the the very first stage you have to do before bringing something to a microcontroller is actually get a model that runs, even on an x86, high-end machine. So I would recommend using whatever you're most comfortable and productive with, in terms of a framework for working with like Python. Then once you actually have a model that's doing what you want in that environment, our whole workflow is based around TensorFlow. But the good news is that it's usually not a crazy amount of work to kind of, if you have been using PyTorch, to create the same model in TensorFlow, because most of the work is usually around like things like getting the training data and figuring out like roughly what architecture and things you want. And then once you're in TensorFlow, then it's a process of, okay, how do I shrink this model down so that it's going to be small enough to fit on my microcontroller? And then going through the export process. And we have a bunch of examples of how to do that for different use cases. We actually have an example of how to recognize movement. I've got this magic wand here that we strap an Arduino to, and you can actually do sort of gesture recognition using the accelerometer. And we also have a simple model that recognizes like yes, no audio using kind of a 20 kilobyte model. So that's another potential way to look at it, is you could actually look in the TensorFlow Lite micro examples folder and kind of start off with something that's recognizing audio, like recognizing yes, no, and then adapt it for your audio that you want to recognize. So that's kind of the other way around of doing it, is saying, hey, I'm not going to try and create my own model. I'm just going to use one of these end-to-end examples and modify it to do what I need to do.
Solving the DSP and go ahead.
Are there any good methods for moving PyTorch models to TensorFlow Lite? Are there any tools?
No.
Okay.
Unfortunately, I mean, there are some. I've seen some open source stuff out there, but it's a tricky problem, because all of these frameworks, TensorFlow has something like over 1,400 different operations that you can actually be using under the hood, and PyTorch is on a similar sort of magnitude, and so writing a converter which handles all of them is really tough. So what happens is you end up with tools that will work for some subset of models to convert them over. Yeah, you just you often don't have a good experience. But honestly, I find that once you've learned one ML framework, it's usually fairly easy to just transfer your training process and your data over to a different one instead. So that's the way that I tend to look at doing this sort of thing.
Are there any shortcuts to doing that, to making that leap over that you would suggest? We have some partners that are leveraging PyTorch today. We need them to move over to TensorFlow Lite, and we want to make that as painless as possible.
So I think I put my email out there.
Okay.
You know, drop me and Ian an email, and we'll be happy to sort of, you know, chat and see in those specific cases how we can help.
Okay, perfect. We'll get them in contact with you. Thanks.
Awesome.
Thanks, Reed. One of the questions from Ram again looks like, yeah, is it possible to use GAN models, GAN models with the current version of TensorFlow Lite? If not, how easy is it to add these architectures into the framework by ourselves?
I have never actually I've never tried to convert a GAN model. So from what I remember, they mostly use like convolutions and transpose convolutions and things like that. So you might well be able to use them with TensorFlow Lite Mobile. You would probably struggle to use them on TF Lite Micro, but it really depends. I've only ever used GAN models for fairly compute-intensive things like image generation. If you have a specific use case, you know, like a product that you're trying to build that needs that sort of capability on microcontroller, we'd love to hear from you because it sounds like a pretty you know, cutting-edge application, and maybe we could actually help you get that going.
And yeah, before we're almost to the top of the hour. I actually did check Pete and Ian if you have a hard stop. We do have a little bit of time we can go over. There's one more question in the chat.
I can go over by a couple of minutes, but I probably have to jump off after that. So
yeah, no, okay, we'll finish off with this question and maybe squeeze one more, but we'll see. What is the best way for a person with zero ML experience to bring ML to their embedded product without being too reliant on third-party software? The idea is to keep things super customizable.
So I don't know if you're worried about being reliant on third-party software in terms of TensorFlow Lite Micro, because avoiding that is going to be tricky. But as long as you don't mind being reliant on one piece of third-party software, TensorFlow Lite Micro is really designed to be very hackable. Like that's been one of our design goals, is that you should be able to like kind of jump in and like customize the code, because we know embedded developers need to do that. You know, you're facing a lot of very tight resource constraints, so you really need to be able to touch the whole stack of code that you're using. As far as getting started with zero ML experience, that's also something that we've really tried to set up the framework to help with. If you look in the TensorFlow Lite Micro examples folders, you'll actually see, or if you actually fire up the Arduino IDE and like plug in your Arduino Nano BLE device, you can actually just choose some of the examples to do things like voice recognition, image recognition, gesture recognition, like I mentioned with the wand. And you don't need to know anything about ML to just use them. And you can even start doing things like retraining them without having to kind of, you know, get a PhD first.
absolutely back that up. It's you know, my machine learning education in university is very ancient, so it's mostly embedded. And I think the hard part of using in the embedded space right now with the way TensorFlow Lite for microcontrollers is coming up with those more of the sensor abstractions or connections. So that's something that's in your sphere of control and influence as an embedded product person. And then the other great thing is it's open source. So yeah, you're dependent on something, but it's also not ever going to be yanked out from underneath you. So. Well, I know we've run a minute past, and I'm sure you've got other meetings too that you're already a little late on. So I really appreciate all of the help today. I think we've also had Pete's email address. Yep, there you go, and Ian and mine, and right above there. So yeah, if you want a further discussion, feel free to contact all of us, and we'll see what really cool applications and experiences you guys are having. We're always looking out for that.
Thanks, Pete and Ian.
Awesome. Thanks, Lee. Thanks, everyone.
Thank you, everyone.